Hey there, physics lovers. It's Mr. Clegg. And we're going to start with number 6 here today on this extra challenging factor label method problem. So the idea here is we want to find out how, we have a flow rate of 85,000 cubic feet per second. We want to find out how many water bottles, 800 milliliter water bottles, could be filled every hour. And this is a big key piece here. So we want to start converting our cubic feet into cubic centimeters. And we have conversion factors for that. And then we're into that is the same thing as milliliters. And then the only other thing we have to do is convert the hours and of course convert it into water bottles. So the reason why I gave you this problem was to show you that it can be you can have very complex calculations and all you need to do is just keep adding steps to your calculation and you can do it. So let's start out with our 85,000 number here, 85,000 cubic feet. That's feet cubed per second. And then we shall start multiplying by conversion factors. I think we could go ahead and convert this cubic feet number right here. Let's go ahead and take cubic feet. We'll start with not cube feet. Let's go to inches. So feet to inches, we know that there are 12 inches in a foot. And now we can cube all of that. So let's cube the 12. Whoops. Cube that. And let's cube the inches, cube the feet. And we can cancel out the cubic feet. Now we got cubic inches. Nice. Now we can go to cubic centimeters. So now we got inches to centimeters. So there's inches to centimeters. And now we have 2.54. I'm a little bit out of space here. The mic smaller. Okay, there we go. 2.54. Come on now. All right, now we can cube that. My tablet glitches out sometimes. I don't know why it does that, but occasionally I have to fix it. So now we got our cubic inches going up into cubic centimeters. And just cube all the conversion factors. Now we got cubic centimeters per second. That's going to be a much bigger number, but same volume. Let's go ahead and keep going so we get all the way to milliliters, right? So we have cubic centimeters now to milliliters. Those are equal. Those are actually the same exact thing. So I'm just going to change that. Um, okay, so now we got milliliters. And now let's just go ahead and convert into water bottles, right? So milliliters per water bottle in this case. So one 800 milliliter water bottle, I guess you could say. I can't fit all that in there, so I'm just going to put WB for water bottle. We have 800 milliliters. We have 800 milliliters per water bottle. Okay. So I'm going to just go ahead and cancel that out. So now we have water bottles per second, but we want to have water bottles per hour, which is going to be an even bigger number. So let's go ahead and just keep adding. Now we're going to take care of that seconds down there. Put seconds up top to minutes. Look at that. 60 seconds in 1 minute. And then we'll do minutes per hour. 60 minutes in 1 hour. Let's cancel out our units. Seconds. We're going to have to do a triple slash or something like that. Triple slash seconds. And then we're going to do triple slash the other way, minutes. There we go. A little messy there, but I think we got the idea that what's not slashed out is water bottles per hour. So that once we get the calculation done, this is a little bit complicated, but it's not too bad. We're going to clear the calculator, 85,000. And this is where this volume calculation thing is so brilliant because I don't care what 12 cubed is. All I do is type 85,000 times 12 cubed, 12 to the power of 3. I don't need to calculate that number. I'll let the calculator do that. Times 2.54 to the power of 3. All right, skip this. I got ones. Now we're going to divide by 800. We're going to times 60. And we're going to times 60 again equals. And we get grand total of 1.083. Let's just leave it at that for now. 0.083 times 10 to the 10th. And this is water bottles per hour. Let's round that though, because we only had two significant figures. So we're going to round it to 1.1 times 10 to the 10th water bottles per hour. All right. Excellent. That was pretty tough, but we just kept at it and added lots and lots of conversion factors, and we got it. Okay, this next one is conceptually a little bit challenging, but the math is a lot easier. So engine displacement in a vehicle in a an engine is just how far the cylinder goes multiplied by its area. So that gives you a volume that cylinder displaces as it goes from its up position to its down position. And it's basically a proxy for how powerful your engine is. A bigger engine displacement gives you more power, typically. Um, so that's the way that works. So it might be tempting to start this with the 3.1 liter number. It's like, what do we start with? 3.1 liters. But we don't have a time in that. So notice that revolutions per minute or rotations per minute is is a time rate. And so we want to start with that because the liters all by itself doesn't, it's actually liters per revolution is what that really is. But I want to start with the time rate here so that I can get that in there. So I'm going to start with 2000 rotations or revolutions. I'm going to call it revolutions actually. Revolutions per minute, 1 minute down here. Right? So we could just go to seconds right away. We want to know how many revolutions per second. It doesn't matter which order you go in. You could do the other one first. But I want to just go ahead and cancel out minutes and go to seconds. So I know that there's 60 seconds in 1 minute. Let's go ahead and cancel that out. So I can do that. And now I have 2000 revolutions per second, but how much volume is that? Well, each revolution, right? So now I can put in one revolution. I know that I have 3.1 liters of volume each time the engine goes around one time, or each time the cylinders all go around once, you get 3.1 liters of displacement. So now I can just, by the way, this whole thing might make more sense when we get into our chapter on energy um, and power and stuff like that. So revolutions. Now we're going to go ahead and just all we have to do is multiply that out. And so we can take our 2000, here we go. We can divide by 60 and multiply by 3.1. Okay, so we got 103.33. Looks like a repeating number here, and that would be liters per second. So we do need to worry about sig figs here a little bit. Let's call that 100 liters per second. That's still a pretty big amount of that's a lot of volume per second. All right. Why did we round it this way? I actually just realized that my 2000 rotations per minute only has one sig fig in it, so my answer only has one as well. Um, we don't get super worried about sig figs in this class, but it could happen. Let's talk about this little thing. How many corn kernels are in 1 gram? This is just a matter of put which one you put on top, right? So if you want to put, uh, you know, um, how many kernels are in 1 gram, right? So you want to say 28 kernels. I'm just going to call it KER kernels per 18 grams. If I do that division here, 28 divided by 18, I'm going to get 1.5 repeating 1.5 repeating. That's what kernels per gram, right? Now we can round that, and we always want to round here. It looks like we have two sig figs, so that would round to 1.6 kernels per gram. So we can round to 1.6 kernels per gram. We could do it the other way around. If we want to know how many grams is in one kernel, we always want to put whichever one is supposed to be one, we put that one on the bottom. So kernels on the bottom, we have 28, we have 18 grams. These are probably not accurate numbers at all. I just made them up. But here you go. If you have 18 grams per kernel, you can do 18 divided by 28, and you're going to get 0.6428, let's call it 29 grams per kernel. And of course, we have to round that to get our good get two sig figs. So now we have 0.64 grams per kernel. And then the cool thing is if let's see, I think I want to, what am I doing here? I just want to tidy that up a little bit. There we go. So, oh geez. Anyway, one of the cool things is if you invert this number 0.642, if you hit the inverse button or 1 over x to the minus 1 or 1 over x, just hit that button and you're going to end up with, if you invert this number, you get that number. If you invert this number, you get that number. So these are inverses of each other, and that hopefully is obvious because the units are. The units are really nice because it helps you to give meaning to what this number is, and it helps you to organize your thinking. So let's just say you had for number 9, let's say you had 298 grams worth of corn in your jar. You wanted to know how many kernels that is. You could use any of these numbers as long as you put the units in the right place, put grams on the bottom and kernels on the top. As long as you do it that way, you could use, um, you know, 18 and 28. Or you could put the unrounded one here. You could put the 0.6429 and 1. Or you could put, 1.5 repeating over 1. You can do any of that. I think in this case, it's probably a little easier just to put my 18 grams and my 28 kernels up here. But either way, any of those would be fine as long as I don't round it before my final answer. I should be fine. So I could go 298. I can go times 28 and divided by 18. It's the same thing. And so I should get my 463.5 repeating, whatever. And that would be kernels. I forgot to cancel out my units here. My grams are canceling out. That's the idea. Oops, there we go. Okay. So now my little zoom thing is getting in the way. I want to round this because I had 3 sig figs here. In reality, I might have had more, but this is the number I got, so we'll round it. So it would be 464 kernels. All right. And I think rounding to the whole number of kernels is probably a smart idea because we're trying to find out how many there are. But the idea is this is a good way to organize your thoughts. You can put your units and really figure out a lot of things that, not that this is that hard, but, keeping your thoughts organized in terms of grams and kernels can be really easy if you label things well and think of it in terms of this. So good luck. I'll see you on the next one, guys. See you later.